You've made it through this far of the school year, and now we've just got one more last thing to learn, and that is multiple dependent events. Last week we looked at independent events, and the probability each time just kind of stayed the same. Now we're looking at dependent events where the probabilities are going to change slightly. So let's take a look at an example first to see what's going on. So you've got this cooler here, and it's filled with a whole bunch of sodas. We got Sprites, we've got Cokes. That's it. Sorry, not a great selection. They should have Dr. Pepper in there or something. But there's some more Cokes than Sprites, and in particular it says that there are 12 Sprites and 22 Cokes. And I want to know, what's the probability that you pick a Coke? So first thing I need to know is I need to know how many total there are. So if there's 12 and 22, that makes 34 total cans of soda. So out of those 34, I'm going to reach in and I'm going to select one, and what's the chance that it's a Coke? Well, there's 22 Cokes in there out of 34 total cans of soda. So all we have to do is divide those. That's 0.6471, which we know as a percent would be 64.71. Just slide that decimal 2 spots. So that isn't dependent probability. That's just basic probability. Now what we're doing is now we're going to take a second soda out of the cooler. So instead of just reaching for one, maybe you're thirsty, maybe you've got a date, but you're going to take out 2 cans of soda. And I want to know, what's the probability that you get 2 Cokes in a row? Both of them are Cokes. So since I'm going to select 2, I'm going to draw 2 slots. I'm picking 2 things. So there's my 2 slots. And now I'm going to reach in, and the chance that that first one is a Coke, well, we already found that one. It's 22 out of 34. So that's the chance that the first one is going to be a Coke. So now what I'm going to do is I'm going to look at this picture here, and I'm going to scribble this one out. We picked that one. Now you'll notice there aren't 34 total to choose from anymore. And there aren't 22 Cokes left anymore because we selected one of them and we took it out. We didn't put it back in. We took that Coke and we put it off to the side. Now we're going to go reach in again. So now when I reach in to select that Coke, there's only 33 left. There's 33 total sodas to choose from, and there's only 21 that are Cokes because we took one on that first draw. So what we have to do now to find the probability of both of them, we just multiply. So we take 22 over 34 times 21 over 33. I'm going to show you how to type this in Desmos. You just take 22 divided by 34, and then you multiply it by 21 divided by 33. And it gives you 0.4118 is what it will round up to. So 0.4118. And you can convert it into a percent, 41.18%. And that's the probability of selecting 2 Cokes in a row. Getting 1 Coke in a row, 65% or so. The chance of getting 2 Cokes in a row, it goes down a little bit. Now we're going to go back to the well one more time. I want to know, what's the chance that you get 3 Cokes in a row? So let's draw 3 slots. And let's just start from the beginning. The chance that you get the first one as a Coke, we knew that was 22 out of 34. But now that Coke is gone. There aren't 22 Cokes left. There's only 21 Cokes out of a total of 33 sodas. So I picked 2 Cokes now. Now I go back one more time. How many Cokes are left? There's 20 left. Out of how many total cans of soda are left? 32. So we're going to multiply 22 over 34 times 21 over 33 times 20 over 32. And I've already done that one for you. It becomes 0.2574, which is 25.74%. So that's the chance of selecting all 3 Cokes. And this next one, we're just going to skip it. You're welcome. When you have multiple dependent events, one of the key phrases that we're talking about with multiple dependent events is without replacement. So I'm going to say without replacement. That's going to be one of the most common ways that you can think of dependent events. You'll notice when you selected that Coke, it was gone. You didn't put it back. So that means without replacement. So when you take one out, now the probability changes and it goes down by 1 each time. So hopefully you notice a pattern. Below is the first probability. Pretend the probability of something happening was 30 out of 50, but now you take it away. How many are left? Well, 29 out of 49. Now you take that one away. How many are going to be left? 28 out of 48. And hopefully you're noticing a pattern. Everything just goes down by 1 each time. And this times 100 here is just to convert it to a percentage for you. So if you were to multiply all of these fractions together, if you were to multiply all of those together, we would end up with 0.0673 approximately. And by doing that times 100, it just moves that decimal over 2 spots for you, so you get 6.73%. I think you kind of get the gist of the next one. We probably don't need to go over it. It's going to be 8 out of 18, 7 out of 17. Every time you select a new one and you don't put it back, it's going to go down by 1. And then the 100 just turns it into a percent for you. So let's take a look at another example. We've got a teacher, and the teacher has 32 calculators, but however, 8 of them are broken for whatever reason. Maybe that solar panel on it doesn't work, maybe the batteries are out, who knows. But you decide to be nice, and you're going to grab 3 calculators at random for yourself and then 2 of your neighbors. So you're going to go pick them up for your friends. What's the probability that all 3 calculators work? So since I'm selecting 3, I'm drawing 3 slots. 1, 2, 3. Now let's take a little inventory of these calculators. I have 32. This is when I total. And 8 of them are broken, which means 24 of them, they're good. So if 8 are broken, 24 of them are going to be good. That gives me a total of 32 calculators. So you're going to reach into that calculator pile, and I'm hoping that it works. What's the chance that the first one's a good one? Well, there's 24 good ones out of a total 32 calculators. So the chance that your first one is good, 24 out of 32. Now, let's say it was a good one. Yippee, it works. How many good ones are left? Well, you just took one of them away, so there's only 23 of them left. And how many total calculators were left? Well, there aren't 32 because you took one. So there's only 31 calculators left. So hopefully that second one was a good one. It was a 23 out of 31 chance. And now you're going to reach in and we want to find the chance of the next one being good. So there aren't 23 good ones left because you just took another one. There's only 22 good ones left out of 30 total left in whatever bucket you're picking these calculators from. So we just take these, multiply them all together, and if you multiply these all together, you've got a 0.4081. If you multiply it by 100, you can get 40.81% chance. So about a 41% chance that you're going to take all these 3 calculators and hey, they're all working. Next example, we're going to go the other way. Let's say we go for rotten luck this time. Instead of having good luck and saying, oh, these calculators are good, what's the probability that all 3 of them do not work? So again, draw 3 slots because we're selecting 3 calculators at random. And now I want to know what's the chance that all 3 of them are broken and they don't work. So what's the chance the first one is broken? There's 8 broken ones out of 32. Now you take that broken one away. How many broken ones are left? 7 out of a total of 31 calculators. Now you take that second broken one. Boy, this is really unlucky. and you take yet another broken one. That's a 6 out of 30 probability. And you can multiply them all together. You get 0.0113, which, if you move the decimal over 2 spots, is 1.13%. It's not going to happen very often. That's a 1%, like 1 in 100 times approximately, that you're going to get all 3 bad calculators. Go ahead, pause the video, try the next 2 on your own. Hopefully, these numbers aren't true, but they probably kind of are. When you're looking at desks in classrooms, a lot of times kids stick their gum in there. Yuck. So go ahead and finish that one, and then we'll move on and do one more example together. So come on back. See you soon. All right, last example, we've got Congress is currently made up of 48 Democrats, 50 Republicans, and 2 independents. I think these numbers are actually a tiny bit off because we just had an election. So this is the Senate. There's 100 Senate seats. So you can total these all up. 48 plus 50 plus 2. There are 100 total senators. Suppose a lobbyist for Amazon. This is how business gets done in this country. You just talk to the politicians and then cut a deal with them, and then, the laws that you want get passed. So suppose some lobbyist for Amazon. Amazon's a pretty powerful company. They go to Congress and they say, hey, you scratch my back, I'll scratch yours. They're going to select 3 senators to sweet talk. So they're just going to pick 3 of them at random. What's the probability that all 3 are Democrats? So we've got 1, 2, 3. So we're going to pick 3 senators. And what's the chance the first one is a Democrat? Well, according to this, how many Democrats are there? 48 out of 100. All right. We sweet talk them. We got them on our side. They're going to do exactly what we want them to do. But I'm not going to sweet talk the same one, so they're out. So now how many Democrats are left to choose from? Well, there's only 47 left out of a total of 99 senators. That one, we get them to do what they want to, so they're done. And now there's only 46 Democrats left out of 98 total senators. And if you multiply them all out, you end up with 0.1212. It repeats, and that would end up being 12.12% if you round it to the nearest hundredth. And now, what's the probability that, we're going to go on the flip side, what's the probability that they select all 3 that are Republicans? So again, we're selecting 3. So since I'm selecting 3, we're going to draw 3 slots. If I were to select 10, I'd draw out 10 slots. So what's the probability all 3 are Republicans? Well, we got to look at how many Republicans there are. There were 50 out of 100 Republicans. Once I get that first one to do what I want, we're done with them. There's only 49 left to choose from out of 99. Once they're done, it's 48 out of 98. Every time you pick one and you don't replace it into that drawing pool, I'm not going to select the same one again. That's a waste of my time. So I'm going to go to a new one every single time. So it drops by 1. And then we're going to multiply all of those together, and we get 0.1070. Now, even though that last one's a 0, just for Schoology purposes, I'm going to write it as 10.7%. If you wrote 10.70%, you'd still be correct. It'd be more significant figures. For this one, 10.7%. So I think there's one similar to that for the answers you put into Schoology this week. So there is just a couple more for you to do on your own. There's a challenge if you'd like to learn about how decks of cards work. So for those of you that are into probability with cards and dice and things like that, go ahead and look at that one as well. And in the next video, we're going to put more of a visual representation to it. So you're going to kind of see why it happens. And we're going to work on those tree diagrams once again. So finish these up, throw them into Schoology, and then go watch that next video.